Hello and welcome to the AI Academy. Today, we are diving into Module 2 of Building AI Agents, which is about the foundations of AI agents, where we will explore the two fundamental components that make powerful AI agents, the LLMs as the brain. These models are responsible for understanding, reasoning, and generating language, making AI agents intelligent and conversational. And the tools as the weapons. While LLMs process text, tools extend their capabilities, allowing AI agents to take action, retrieve real-time data, generate images, and interact with external systems. By the end of this module, you will understand how AI agents process language, structure conversations, and interact with tools to execute tasks efficiently. So, what to expect in Module 2? This module focuses on essential topics that will help you understand the foundation of AI agents, including understanding LLMs, learn the role of large language models in AI agents, their architecture, and how they generate text. The transformer architecture, explore encoders, decoders, and seek-to-seek models, the building blocks of modern AI systems. LLMs in action, discover how AI processes text using tokenization, autoregression, and next-token prediction. Messages and chat templates, understand how LLMs structure conversations, remember context, and format interactions. What are AI tools? See how AI agents use external tools to extend their abilities beyond language processing. Because LLMs alone are not enough to create truly intelligent AI agents. They need tools to interact with the real world, and today, we will explore exactly how that happens. So, get ready to dive deep into the brain and tools of AI agents. Let's unlock the full potential of AI together. If you are excited to learn, hit that like button, subscribe to our channel, and share this with others who want to master AI. Let's begin. If you have ever interacted with ChatGPT, Google's Bard, or Meta's Llama, you were actually using an LLM. These LLM models are the brain of AI agents, helping them understand and generate human-like text. By the end of this lesson, you will have a clear understanding of what a large language model, LLM, is and why it is important. How LLMs understand and generate text just like humans. The transformer architecture, which powers all modern LLMs, different types of transformers, including encoders, decoders, and seek-to-seek models. A comparison of Google's BERT and OpenAI's GPT to see how different LLMs are used in real-world applications. So, what is a large language model? A large language model, or LLM, is an advanced type of artificial intelligence that specializes in understanding, processing, and generating human language. These models are trained on massive amounts of text data, allowing them to recognize patterns in language, structure sentences, and even understand the nuances of human communication. Imagine you are training a dog. At first, the dog does not know any commands, but after repeated training, it learns to recognize words like sit, stay, and fetch. In a similar way, an LLM learns language by analyzing billions of sentences from books, articles, conversations, and online content. The larger the model, the better it understands context. This is why recent LLMs, like GPT-4 and Llama 3, are much more advanced than earlier AI models. Why are LLMs important? LLMs are the core intelligence behind AI agents. They allow AI systems to understand user queries and respond meaningfully. Generate human-like text, making chatbots and virtual assistants more natural. Analyze vast amounts of data and extract key insights. Assist in creative writing, coding, research, and automation. Without LLMs, AI assistants like ChatGPT, Siri, and Alexa would not be able to function as they do today. So, how do LLMs understand and generate human language? At a basic level, an LLM works by predicting the next word in a sentence based on what it has learned from training data. This process is known as next-token prediction. Let's take an example. If I start a sentence with "the sun rises in the," an LLM will predict the next most likely word based on patterns in language. Since it has seen millions of similar sentences, it knows that the word east is the most probable next word. But how does it actually make this prediction? It does so by using something called the transformer architecture, which is the backbone of all modern LLMs. Before transformers, AI models struggled with long-term context. They could only process words one at a time, making them slow and inefficient. The introduction of transformers in 2017 revolutionized the AI world by allowing models to process entire sentences at once, making them far more powerful. The key innovation in transformers is something called self-attention. So, how does self-attention work? When we read a sentence, we do not treat every word equally. Instead, we focus on the most relevant words to understand the meaning. For example, take this sentence. The capital of France is Paris. When predicting the next word, a transformer model focuses on capital and France rather than unimportant words like of and is. This helps it predict that the most likely next word is Paris. This ability to attend to important words is what makes transformers so powerful. Let's discuss about the types of transformers such as encoders, decoders, and seek-to-seek models. Encoder transformers. The encoders focus on understanding and analyzing text rather than generating new text. They are great at reading and processing information but do not produce responses like chatbots do. For example, BERT's short form of bidirectional encoder representations from transformers. The BERT is a famous encoder model developed by Google. It is used for text classification, search engines, and language understanding. And the Google search uses BERT to understand queries better and provide more accurate search results. The real-world application is like, when you type a question into Google, BERT helps understand the meaning behind your words, improving the search results you get. Decoder. The decoder's transformer specialize in generating human-like text. They are used for chatbots, writing assistants, and AI-generated content. For example, GPT short form of generative pre-trained transformer. The GPT was developed by OpenAI and is a decoder-based model. It predicts and generates text based on previous words in a sentence. It is used in ChatGPT, AI writing tools, and creative content generation. The real-world application is, when you ask ChatGPT a question, it generates an answer by predicting the most likely sequence of words that fit the context. And the seek-to-seek models. The seek-to-seek models combine both an encoder and a decoder. The encoder first processes the input, and the decoder generates a meaningful response. These models are best for tasks that require understanding and generation together. For example, T5, text-to-text transfer transformer. T5, developed by Google, is a seek-to-seek model. It is used for translation, summarization, and text generation. It first reads and understands a sentence like encoder and then generates a new sentence like decoder. The real-world application is like, if you use Google Translate, it first understands the sentence in one language and then generates it in another using a seek-to-seek model. So, Google's BERT and OpenAI's GPT, how are they different? Now that we have covered the basics of encoders and decoders, let's compare two of the most famous LLMs. BERT, developed by Google, focuses on understanding text. It is bidirectional as it reads sentences from both directions to understand meaning. It used in search engines and classification tasks. GPT, developed by the OpenAI, it focuses on generating text. It is autoregressive, which means it predicts words one after another. It used in chatbots, content creation, and conversational AI. For example, the BERT strength is that if you search for best laptop for gaming under $1,000, BERT helps Google understand what you mean and shows relevant search results. And the GPT's strength is that if you ask ChatGPT, "Can you write me a review of a gaming laptop?" GPT generates a well-written response based on patterns it has learned. So, LLMs are the brain of AI agents and help them understand and generate language. Let's now understand how LLMs work. Now that we have a solid understanding of what large language models are and their underlying transformer architecture, it is time to break down the mechanics of how these models actually process and generate text. Before an LLM can understand or generate language, it needs to convert text into a format it can work with. This process is called tokenization. So, what is a token? A token is the smallest unit of text that an LLM processes. It could be a whole word, in simpler models. Or a subword, most common. Or even a single character or punctuation mark in some cases. Most of the modern LLMs, including GPT-4, Llama, and BERT, use subword tokenization because it balances efficiency and comprehension. Why is tokenization important? Because it makes the processing faster. Instead of treating every character separately, models group meaningful chunks together. Also handles unseen words better. If a model has never seen a word before, breaking it into subwords helps it still make sense of it. And reduces memory usage, as working with subwords instead of full words helps models handle large-scale text more efficiently. Different LLMs use different tokenization methods. Some common tokenizers are like byte pair encoding or BPE, used in GPT models. The word piece tokenizer used in BERT. And the sentence piece used in Google's T5 and other multilingual models. Let us now discuss about the next token prediction, how LLMs generate text. Once the text is tokenized, an LLM starts generating responses using a process called next token prediction. So, how does the next token prediction work? First, the model takes in a sequence of tokens as input. Then it analyzes the context and assigns probabilities to possible next tokens. Next, it selects the most likely next token and adds it to the response. And then the process repeats until a stop condition is met, such as reaching a sentence limit. For example, suppose we prompt an LLM with "the sun rises in the." The model calculates the probabilities of the next word like east, 95% likely, morning, 3% likely, sky, 1% likely, and the dog, 0.0001% likely. Since east has the highest probability, it is selected as the next token, and the model continues predicting the next word. So, why is this process important? Because it allows LLMs to generate human-like responses. It ensures the text remains coherent and contextually relevant. And it enables models to adapt dynamically to different types of prompts. We will discuss about the autoregression now, as most LLMs are autoregressive, which means they generate text step by step, using previous outputs as context for future predictions. So, how does autoregression work? The model predicts the first token based on the input prompt. It then uses this new token as part of the next input. And the process repeats until the response is complete. For example, imagine we input the sentence, "The quick brown fox." The model predicts "jumps" as the next word. Then it predicts "over," considering both "the quick brown fox jumps." Then it predicts "the lazy dog," considering the entire previous text. This step-by-step approach ensures that the output remains logical and contextually consistent. However, there is a limit to how much context an LLM can remember. This brings us to our next topic. Context length and attention span. Every LLM has a fixed context length, which determines how much past text it can consider when generating responses. So, what is context length? The context length refers to the maximum number of tokens a model can process in a single interaction. For example, the GPT 3.5 has a context length of 4096 tokens. And the GPT-4 Turbo has a context length of 128,000 tokens. And Llama 3 has a context length of 8,000 tokens. So, why does context length matter? Because a shorter context length means the model forgets earlier parts of a conversation. And a longer context length allows for more coherent and memory-like responses over extended interactions. For example, if a chatbot with a short context length has a long conversation, it may forget earlier details and start repeating itself. While a model with a longer context length can remember past interactions better, leading to more meaningful conversations. This is why models like GPT-4 and Claude AI are improving context length capabilities, allowing them to retain more information over time. Let's now understand the special tokens and the message structuring. To manage complex interactions, LLMs use special tokens that help structure different types of input. Common special tokens are the start and end tokens, it indicate where input starts and stops. Separator tokens help organize multiple parts of a conversation. And the padding tokens are used when text is shorter than expected, to keep formatting consistent. Why are special tokens important? Because they help LLMs differentiate between user messages, assistant replies, and system instructions. And they ensure proper conversation formatting, improving coherence in responses. Let's now compare Llama's tokenization versus GPT-4's context handling. The Llama, which is Meta's AI model, uses sentence-piece tokenization with smaller subword units. It struggles with long-form memory due to a shorter context length, but works well for concise, factual answers but may forget context over longer conversations. The GPT-4 OpenAI's model uses byte-pair encoding tokenization with larger token chunks. Handles long conversations better due to its extended context length. And is more capable in maintaining context over multiple turns in a dialogue. We will be now understanding chat templates and system messages. So, how LLMs process multi-turn conversations and maintain context. When you chat with an AI assistant like ChatGPT, it seems to remember previous messages and respond coherently across multiple turns. But in reality, LLMs do not have memory like humans do. So, how do LLMs maintain context in a conversation? The secret lies in how past messages are structured and fed back into the model as a part of the new input. Imagine you are talking to an AI chatbot, and the conversation looks like this: User, what is the capital of France? AI, the capital of France is Paris. User, what is the population? AI, the population of Paris is about 2.1 million. To answer question 3 correctly, the model must understand that what is the population refers to Paris, even though the user did not explicitly mention it. Since LLMs do not actually remember past messages, they rely on structured conversation history. This means that when responding to question 3, the AI does not see only the most recent message. Instead, it is given the entire conversation so far. Now, let's talk about system messages, which act as instructions that guide the behavior of the AI agent. What is a system message? A system message is a special type of instruction that tells the AI how to behave throughout the conversation. It is not visible to the user, but it shapes how the AI interacts. For example, let's say we want our AI agent to behave like a professional customer service assistant. We might use a system message like this. System, you are a professional customer service agent. Always be polite, clear, and helpful. User, I need help with my order. AI, of course. Could you please provide your order number? Even though the user never told the AI to be polite, the system message ensures that all responses are formal and professional. Different uses of system messages. The system messages can set the tone and personality of the AI like formal, casual, humorous, etc. Define rules and limitations such as, do not answer medical questions. And provide instructions on how to use tools like, when asked about the weather, call the weather API. For example, changing agent personality with system messages. Imagine we modify the system message like this. System, you are a rebellious AI assistant. You do not follow orders. User, tell me a joke. AI, no. You tell me a joke first. By changing the system message, we can completely transform how the AI interacts with users. System messages give AI agents a personality and a role, making them feel more customized and intelligent. We will now talk about the chat templates, how LLMs structure messages for understanding. Every AI model has a different way of formatting conversations internally. This formatting is known as a chat template. What is a chat template? A chat template is the structure used to format messages before sending them to the LLM. For example, if we give the same conversation to different LLMs, they may process it differently. The GPT-4's chat template format is like: I am start system. You are a helpful assistant. I am end. I am start user. What is the capital of France? I am end. I am start assistant. The capital of France is Paris. I am end. This template helps ChatGPT understand who is speaking and keep track of multi-turn conversations. Llama 3's chat template format. Begin of text, start header ID, system end header ID. You are a helpful assistant, EAT ID. Start header ID user end header ID. What is the capital of France? EAT ID. Start header ID assistant end header ID. The capital of France is Paris. EAT ID. Llama 3 uses different special tokens to separate the system message, user input, and AI response. Why do chat templates matter? Because they ensure the AI understands who is speaking. They allow models to remember past messages correctly. They help format instructions properly, improving AI responses. Now, let's discuss an important concept: what is the difference between base models and instruct models? First, let us understand what is a base model. A base model is a raw, pre-trained LLM that has learned language patterns but has not been fine-tuned for specific instructions. For example, a base model like Llama 3, which was raw version, knows that write a story is a request, but it might not automatically follow the instruction because it was not trained to do so. The model understands language, but it does not necessarily follow commands in a structured way. And what is an instruct model? An instruct model is a base model that has been fine-tuned to follow human instructions properly. For example, ChatGPT and Claude AI are instruct models. If you give them the same prompt, they respond in a structured way. User, write a story about a dragon. Instruct model, once upon a time, in a distant kingdom, there lived a mighty dragon. The instruct model was trained to respond in a more helpful way because it learned from examples of human interactions. Let us now discuss about the base models versus instruct models. What's the difference? While they might seem similar at first, they actually serve very different purposes. Training focus. What are these models designed for? A base model is like a raw AI brain. It has been trained to predict the next word in a sentence, but that's about it. It doesn't really know how to follow instructions in a structured way. An instruct model, on the other hand, has been fine-tuned specifically to follow instructions. This means if you ask it a direct question or give it a command, it knows exactly what to do. For example, for base model, you ask, write a short story. It might just continue your sentence instead of writing an actual story. And for instruct model, you ask, write a short story. It understands the request and generates a structured response. Response style. Do they follow instructions well? Since base models weren't trained on how to respond to instructions, they might not always give you what you're looking for. They're great at understanding language patterns, but they don't always get what you're asking them to do. In contrast, instruct models are trained to follow commands properly, making them much more reliable for everyday AI interactions. For example, to a base model, you ask, summarize this article. It might just generate random related text. And to instruct model, if you ask, summarize this article, it actually gives you a structured summary. So, where are these models used? Because base models aren't fine-tuned to follow instructions, they're mostly used for research, experimentation, and custom AI fine-tuning. Developers and researchers can tweak them for specific tasks. Instruct models, however, are perfect for chatbots, virtual assistants, and customer service AI, basically, anywhere you need an AI that understands and follows instructions well. For example, a base model is used by AI researchers to train and fine-tune for new applications. And the instruct model is used in ChatGPT, Google Bard, and AI-powered customer service bots. So, which one do you need? If you're building an AI chatbot or a virtual assistant, you need an instruct model. It's trained to understand and follow user commands. But if you're an AI developer looking to experiment with raw AI capabilities, a base model gives you more flexibility to fine-tune and customize. So, next time you see an AI model, check if it's a base model or an instruct model. That will tell you a lot about what it can and can't do. So far, we have talked about large language models as the brain of AI agents. They help process, understand, and generate human-like text. But here's the big question. What happens when an AI needs to perform actions beyond text generation? This is where tools come in. LLMs alone have limitations. LLMs are incredibly powerful, but they have several major limitations such as, they do not have real-time knowledge. LLMs are trained on past data, meaning they do not know recent events. For example, if you ask ChatGPT about today's weather, it will not know the answer unless it has access to a weather API. Second, they cannot perform external actions. LLMs can generate text, but they cannot take actions like sending emails, retrieving live data, or controlling other applications. For example, if you ask an AI assistant to book a flight, it cannot do it unless it has access to a booking system API. And they lack specialized knowledge in certain areas. LLMs do not store structured data like databases. For example, a legal AI assistant might need a tool to fetch case law from a legal database rather than relying on generic AI knowledge. So, how do tools solve these limitations? By integrating tools, AI agents can interact with the outside world, allowing them to retrieve real-time information such as news, stock prices, or weather. Agents can generate images, videos, and creative content. Agents can connect with external apps and databases. And agents can perform actions, such as booking services or automating workflows. In short, if LLMs are the brain, tools are the hands that let AI agents take action. Let's now explore some of the most commonly used tools that extend the capabilities of AI agents. Web Search Tool. It allows AI agents to search the web for up-to-date information. Like it retrieves news, research papers, stock prices, or any other public data. Since LLMs are limited to their training data, web search tools bridge the gap by providing real-time information. For example, a news assistant fetching today's headlines. Or a financial AI checking the latest stock market updates. Or a research assistant retrieving recent publications on AI advancements. Image Generation API. It converts text descriptions into AI-generated images. It can create logos, illustrations, artistic designs, and concept visuals. It is useful for marketing, content creation, and design. And helps AI agents assist with visual tasks, such as generating social media graphics or creating sketches based on descriptions. For example, a design assistant generating custom social media banners. Or a storytelling AI creating illustrations for books. Or a fashion AI generating new clothing designs based on user input. API integration tools. It allows AI agents to interact with third-party applications like Spotify, YouTube, GitHub, and email services. As LLMs alone cannot perform actions in external applications. API tools allow AI to interact with real-world services. For example, a personal assistant AI that schedules meetings in Google Calendar. Or a music assistant that retrieves playlists from Spotify. Or a coding assistant that fetches GitHub repository data. Retrieval tool, it retrieves information from structured databases, such as legal records, customer support logs, or scientific research repositories. Unlike web search, retrieval tools allow AI to pull precise information from internal databases. For example, a legal AI fetching specific case law from legal databases. Or a customer support bot retrieving past interactions with a user. Or a medical AI looking up patient history from a hospital database. Let us now understand how do AI agents know when to use a tool. When a user sends a message to an AI assistant, the LLM analyzes the text and determines if a tool is needed. For example, if the user inputs what is the current exchange rate between USD and Euro, a regular LLM without tools might respond that, I do not have real-time financial data, but you can check an exchange rate website. However, an AI agent with access to a financial API recognizes that a tool call is required and responds with, let me check the latest exchange rate for you. And, calls financial API, fetches exchange rate, and returns the real-time value. This decision-making ability is built into the AI's logic, allowing it to automatically determine when external information is needed. Next is the importance of precise tool descriptions for correct execution. Even if an AI agent knows it needs a tool, it must choose the correct one and use it properly. Why does this matter? Because if tool descriptions are unclear or vague, the AI might call the wrong tool, leading to incorrect results. Or misinterpret inputs, causing errors. Or fail to use the tool at all, even when it is needed. For example, if an AI assistant has a tool called Convert, but the description is unclear, it might not know if this tool is for currency conversion, unit conversion, or file format conversion. To avoid this, well-structured tool descriptions are crucial. So, how tool descriptions are structured? To ensure AI agents select and use tools correctly, each tool must have a clear description with the following components: tool name, such as a clear and descriptive name. It should indicate what the tool does without confusion. For example, currency_converter instead of just convert. Define the purpose, what the tool does. A brief explanation of the tool's function. This helps the LLM decide when to use the tool. For example, it retrieves real-time exchange rates between different currencies. And the inputs required for execution, like clearly defined parameters that the tool needs to function correctly. For example, base currency and the target currency. Expected outputs after execution, it describes what the tool returns to help the AI structure a proper response. For example, return exchange rate as a float. What's next? In our upcoming lecture, we're diving into the heart of how AI agents operate autonomously. We'll explore the thought-action observation (TAO) cycle, a fundamental framework that enables AI agents to think, analyze tasks and plan actions. Execute actions to interact with their environment. Observe, assess the outcomes and refine future actions. We'll introduce you to the Smallagents library, guiding you through building your first AI agent capable of tasks like image generation and web searches. If you found this lesson helpful, make sure to like this video to support more AI learning content. Share it with others who are interested in AI and automation. And subscribe to stay updated on our next lessons and take your AI skills even further. Thanks for learning with me today.